In this video, we will walk through distributed training on the Hopsworks platform using the MNIST example, and we're going to look at CollectiveAllReduce, which is a bandwidth optimal approach to doing synchronous stochastic gradient descent. So on this cluster, I'm just going to log in. I've already got a lot of projects here, as we can see, and I'm just going to find one called Demo Deep Learning, and I'm going to go into that project. So in this particular cluster, we have quite a number of GPUs. We've got 22 GPUs available, and I'm going to go to Jupyter up here, and within Jupyter I'm going to actually shut down the one I'm running already, and we shut down our notebook, not just stop the application. And what I'm going to do is I'm going to select distributed training. And in this particular example, I'm going to train with, let's say, 16 GPUs from the 22. So I'm going to set the amount of memory to our driver to being 4 gigabytes. 4 gigabytes per executor is fine. And the distribution strategy from TensorFlow that we're going to select will be CollectiveAllReduce. Now there are other strategies, mirrored strategy for training when all your GPUs are available on the same host. But if they're not all potentially on the same host, if they're in different hosts around your cluster, then you'll need to go with either parameter strategy, which is not bandwidth optimal. The parameter servers end up being bottlenecks pretty quickly after just a couple of GPUs. So typically CollectiveAllReduce will be the strategy you'll want to use when you have lots of GPUs to train with. So in this case, I'm going to pick 16 workers, and I'm going to have 1 GPU per worker. So what that will give us is a driver here. The driver will launch these 16 executors here, but there won't be one of them. There's going to be 16 of them. Okay, and these, if we look at these executors, they're actually going to order themselves into a ring, and they're going to share their gradients with the other executors in the ring, and they'll do it synchronously. So they're going to block while waiting for updates from neighbors, and the driver will start all of these executors and give them the GPUs. So that's CollectiveAllReduce, and all the executors you can see are using both their upload bandwidth and also their download bandwidth, and that's why we say it's bandwidth optimal. So let's start a notebook with this setup. The GPUs, this is a shared cluster, so the GPUs are still available right now. Somebody could jump in ahead of me and grab them. And I'm going to go to distributed training. I'm going to select a notebook from within distributed training. There's a bunch of notebooks here, and I'm going to select the CollectiveAllReduce strategy that I mentioned with MNIST. And yeah, that was one I opened just a few minutes ago. So I'm going to just start this running. Try and get our GPUs before anyone else does. And then I'll talk through the example. So in this particular example, we can see we have a function here called CollectiveAllReduce MNIST. It's not hyperparameter optimization, so we don't pass in any hyperparameters. Typically you would go through a stage of doing hyperparameter optimization where you would find good hyperparameters, but we're just going to bake in the hyperparameters into our algorithm itself. Assume you've discovered good hyperparameters already. Now the first thing to notice in distributed training, the code is very similar to some of the examples that we've covered previously. This is TensorFlow, it's not Keras, but it's a convolutional neural network. We can see here we've got some conv layers. And if we go further down, you'll see that this is actually using the estimator API that we covered in the hyperparameter optimization video. So we can see here that we've got the estimator API, but what's different here is that we have to specify our distribution strategy. So in this case we're using CollectiveAllReduce, and we can see that the number of GPUs per worker, we're getting this from hops. We have a call called devices.getNumber of GPUs. It will tell you that, so that's nice. And yeah, so then if we go further down, we'll see that it's basically calling the estimator train and evaluate function to to train that estimator. So what Hops will do is it will set up the ring, build up the ring, and then each executor will run this code. And so that means basically we're going to have this ring with executors. We have another executor here, and another one here, and so on. And each executor will in fact get this environment variable called tfconfig. So if you were to run this without Hopsworks and without our support for Spark, you would have to put in the IP addresses of each executor, the ports, and other information about the cluster to set it up. So Hopsworks sets this up automatically for you, and it's accessible within your within your worker or executor in this case. And we can find out things like the total number of workers, what the index of this particular worker or task is, and we can use those environment variables to later on in the code to do different things. So if we go further down, we can see this is our function, and the function is factored into nested functions to make it easier to read and debug. And it's using the TF records format we can see here. But if we go further down, we can see that the code for launching this experiment is quite straightforward. It's really just calling experiment.CollectiveAllReduce, and then this is the name of our training function, collective_all_reduce_mnest. And this example is finished, and let's go back to the Hopsworks UI, and let's open up our application UI and go to the Spark Executors tab. So in here we'll be able to see all of the executors, and we can see that they've all actually finished, so they've all freed up. So we now have freed up all those GPUs back to the cluster. And we can see that there were in total 16 of these executors that were allocated. And we can go and look at their logs, and we can see, you know, this task took 1 minute 16 seconds to complete. And you can go into any of them and check out their individual logs. And we can see they were using 1080 Ti GPUs as well in this case. So the output of this training run, just like for a normal experiment, will be available in the experiment section here, but you can also go and look in the file system to get your output there. And we can go in there and we can see that for this run we had quite a lot of output, but it's a shared file system, so all of these different executors are writing to the same folder. In this case, in distributed training, you will have a chief worker that will be responsible for checkpointing, and that chief worker will write out the checkpoints. So the experiment is available here as well, and we can see it here, and it succeeded. And that concludes this demonstration of CollectiveAllReduce in Hopsworks.